Can you guys see this like slide, the screen?
Yes.
Yes, it is visible.
Cool. So I'll go ahead and get started. And at least what I'm calling this is how to become a senior engineer because, well, hello everybody, welcome. This is how to become a senior engineer, episode one, and it's going to be the intro to test-driven development. So I'll go ahead and explain what this means. So first off, who am I? And sort of like the question also is why should you care what I have to say? But basically, what I realized is I went to MIT and there I did physics and computer science, and they actually trained me on all of the best engineering practices for software construction. And I think it's information that is super valuable and not many other people have. And then beyond that, I also worked at like some of the big tech companies like Google and Northrop Grumman. So I got to see their systems as well. So I've had some exposure to the really proper engineering systems. And to me, that is what separates a junior engineer who might know how to code versus a senior engineer who knows how to architect and lead a team and be part of a team really effectively, and therefore ultimately build much more complicated things. So that's the purpose of these little courses. Let me also say now I'm the founder of a company called Mora AI, and we have two engineers here, Gitesh and Rajeev. Hey guys, you can feel free to interrupt, say ask any questions, say whatever you want at any time, by the way. But yeah, so the purpose
Okay.
is awesome. The purpose is they are currently junior engineers, I would say, but we will train them kind of as a part of Mora because they're part of Mora as well. We will train them to become senior engineers, and also everyone else watching the videos to go from junior, which means you know how to code and you're pretty good at coding. You understand runtime, a few different programming languages, all the basic concepts. So that's where you should be to start out with this course. But then to go from there to truly becoming a senior engineer and be able to build some really solid software. So let's go ahead and get started. I think an important place to start is to maybe take a second to think about what does it actually mean to program? What is programming? And to me, programming is all about building clarity. So, of course, the end result of programming is you have an application that can be used, and they can be applications that are simple to applications that are extremely complex to build. But that's the end result. In the beginning, all you have are vague ideas, a bunch of vague ideas. So you have some product ideas of different features, how they could work, how they could interact. You have some vague notions of different technologies that would be used to implement these features, but it's all this jumbled mess. So I really think that programming is the process of going from this jumbled mess of different ideas in our head into a very structured and explicit way of thinking about it. And ultimately, it's so explicit that you can actually literally put it in instructions for a computer to understand, because a computer can only understand very direct instructions. So programming is the process from just notions in your head over to literal description that a computer can understand in code. And then whatever programming language you choose to use is downstream of that. So that's the vague idea of what's programming. I think it's also important to discuss different kinds of programming. So I think there's two main types of programming people do. I put them here as prototyping and then production building. So prototyping is when you don't fully think through all the questions in your head and you're just building as you go. It's pretty fun. You're having a good time. New ideas come in and you just start coding them. When you do that, you can make progress quickly, but your code base will very soon become a total mess, basically. I mean, you will stop being able to understand it, much less other people on a team. So prototyping usually can't be that style of coding doesn't work for anything too complex. So that's where production building comes in. And the difference between prototyping and building something for real production is that production systems and production code bases are super neat, super organized, easily readable. A lot of times the code is almost the documentation itself. That's how neat the code should be. People say that sometimes. And ultimately, prototyping is very fun. I would say production building, it's also fun in its own way, but it's a lot harder. It's a lot slower. And you have to be a lot more deliberate about every little thing that you do because you essentially don't want to make additions to the code that aren't necessary because every little addition adds complexity and you're always fighting complexity in the code base. That is what limits applications. Powerful applications, that's what limits them from being built is too much complexity to be able to actually build it. So that ties back into our original theme here, which is what is programming? You go from complexity to order. That's ultimately what programming is all about. So this is straight from an MIT course, which is I put the link here, but that's the version in 2016. I took the version in 2020, and I recommend people find the most up-to-date version. But it's called Elements of Software Construction. At least that's what it was when I took it. So in that course, they teach you all about what it means to write good code, and it basically breaks down to these 3 points. Ultimately, good code needs to be in. This is in priority as well. So number one, most important, it needs to be SFB, safe from bugs. That basically means it works. The code has to work. Whatever definition you had of the intended behavior, that is what the code has to do. So that's the most important thing. The second most important is that it has to be easy to understand. So when you read the code, it should be immediately obvious what is going on there. A properly written code is that way. You can almost just read it and understand very nicely. And the way you do that is through proper abstractions. And we can get into that later in the series as well. And then finally, it needs to be RFC, ready for change. So to me, ETU and RFC, these are terms that they use in that course, but to me, ETU and RFC are almost the same. Code that is really simple and really organized and easy to understand is easy to change. It is easy to reuse. So you should always build it in a way that's very easy for people to understand so they can work with it in other systems within the code base or change it if they have to change it, which are very common things that happen. So I hope like a theme that you guys are picking up on already is that you shouldn't just code without thinking about what you're doing. The process of writing code into a code base itself is almost like a product. You are creating something for the other engineers to see. And that code itself, it's like writing. You know, when you write a book, you want to write a really good book. You have to be like clever and careful with what you choose to use. And that's just the same with code.
That was a very good analogy.
Thanks, man. So, what is the process that you can actually use to write good code? This is also straight from that class, from 60. It was 6031 when I took it. Now they call it six. I think 6005 is what they call it now again. Anyways, what is the process for making good code? So this is called test-driven development, and they were very adamant that it's the best way to write code. And generally, I think it is too. So since we're focusing mostly on front end here, we don't really write too many tests like using, we don't write unit tests that often because in front end it's UIs and the UIs you actually have to test them yourself rather than algorithmically for the most part. With other types of code, you can write algorithmic tests, but the idea is the same that you should start with the tests. So that's number one. The first thing you should do is pay attention to what are the product requirements? What is this supposed to do? So, for example, if we're building a drag and drop task list, which is something Gitesh and I were working on before, the very first thing we want to do is think, how should this list work? And you want to think of every edge case possible. I'll get to it in the end, but it's almost like you're in a bit of a competition with the user because the user might use your product in ways that you never intended just by accident. So you have to be more clever in a way than what they possibly could be and make sure you cover all of the cases. So, for example, if you're paying attention to edge cases in a drag and drop list, you might think they grab an item, where do they drag it from? When they drag it into another item, does that create a sub item or does it go under it? What happens if they drag under? What happens if there's a sub item, it has a parent, and you reparent it and give it another parent? So you want to think about every possible outcome and define what that is first. So you define the intended behavior first. Then, before getting into code, I won't go into so much detail for all of these because I want these to be like 15-minute to 20-minute videos. So today we'll mainly just focus on the testing. So what I think we should do first, before making any code changes, is always write a testing PRD. So product requirement documents, that's what they did at Google and what they do at various other big tech companies. Basically, a more business side person, so like a PM, will write all of the requirements in vague, broad terms of how the product should work. But as engineers, I think we should go a bit beyond that and actually create this document that I want to call a testing PRD, so a TPRD. And that is more like instead of vaguely describing how the feature should work, we should really get into the test cases, basically, like all of the different behaviors we expect, maybe in a bullet point list. So that's the step one is define how it needs to work. Once you understand how it needs to work, what we should do is then start going into algorithms. So now you can create algorithms, almost like pseudocode or concepts, mathematical concepts, to specifically start to describe in language how this feature needs to work. And then with those algorithms, we can put it into a design document, which is another thing I got from Google. In Google, they always create PRDs and design documents. The design documents are made by engineers, and they're very specifically like every little function, every file, every component. It gets into what the parts of the code are and what they do. But it's obviously not code yet, but it is describing what are we going to put in the code and then doing pseudocode or algorithms to determine how these things interact with each other. So it's still one step above the code, but it's all of the concepts, all of the files, components, and the ideas. And then finally, by the way, these are all iterative processes. So the whole team will first talk about the PRD and how it should work. They'll come to an agreement there. Once that's pretty finalized, they'll go into the algorithms and the design. They'll discuss that through and through and through until they come to a conclusion on how it should work. Once that's complete and there's sort of alignment on all of these steps, we go into the actual engineering, which is the part that we're all familiar with today. But the engineering should be easy at that point because you actually have all of the algorithms laid out, all of the components that you know you're going to make, even maybe important variables will be defined and their schemas will be defined. And things like TypeScript allow you to define schemas ahead of time, specifically for these kinds of reasons. So I mentioned this a little before, but basically the whole process is collaborative. I said that on the last slide. I guess it was supposed to be on this slide. But at every point, so when you're making the TPRD, when you're making the design document, and then when you're making the code, it's always supposed to be collaborative. Every team member should agree on what to do before moving on to the next point. And then I have a little note here, which is the final pull requests, the final PRs, which is the code itself, through this process should be very safe from bugs, easy to understand, and ready for change. They should be simple, elegant, understandable by the whole team, small, because everyone will have done a lot of thinking already about how to make them really nice before actually coding them in. So to get into a bit more detail, so we talked about like the overall process, like the broad process. Now we can kind of spend a few minutes to talk about the specific. So this is, I know it's a lot of information all at once. It's a bit of a crash course, I think, but I hope it's being useful and feel free to like interrupt me, ask any questions, whatever you'd like. We just have a few more minutes left because I really want these to be pretty short videos. So just a few minutes on a bit more on the TPRD and what it should look like. So the first thing that any of us have to do, and this is also my personal process, the first thing any of us have to do before actually going into code is define the requirements of the feature. So we'll have some idea of what we want to code. Like if I want to go back to this task list example, we have some idea of what it is, but we need to define specifically how it should function in every possible case that we can imagine. And if we can write that down, that's actually really great. It's what tests would be in a different code base. But for front end, again, the tests, we have to do them manually. So you can even imagine like this testing PRD is all of the use cases that we're going to test after we build it to assure quality. And then it's almost like if somebody makes a change to the code, they should go back to the tests and run through them all themselves. Like a QA team could do this in the future, a quality assurance team. They should go through all of those test cases themselves and do it manually to make sure that none of their changes broke the existing behavior. So that's for keeping the code safe from bugs, basically. So we think of all the possible test cases, write them down in the document, and especially try to think of the edge cases. The main guiding behavior in this stage for me is always what behavior do we need this to have? So you're designing how it should function, and you should always ask yourself, how should this work? What should this do? It's almost product thinking, right? So it goes a little bit into the design side, but a good engineer should be able to go a little bit into the design side, in my opinion, especially like a senior engineer. And again, as all documents, we'll iterate on these until the team is on board with it. Here's a list. You guys can just like, there will be a video after, and I'll send it to you. So you can all just like screenshot or pause here and read them, but they're just some tips that I think are useful maybe for making a good a good TPRD, and I might make more of these as well. But I don't have to go into them right now. I mean, the one I do want to mention though is this diagrams tip. So actually, diagrams, drawings, sketches, mock-ups, real product designers, they only work in Figma, right? So, or usually they mainly work in Figma. So they're making mocks all the time. Mocks are super helpful, even as engineers. Even if you don't know Figma, that's fine. When I'm doing this, like I'm all the time on my iPad, all the time using Apple Pencil to draw stuff, make diagrams. I found that to be super helpful when doing the UX, basically. This could be considered the UX of the product. But then you go from UX into engineering with defining the test cases in the TPRD. So that's just one that I want to highlight. So this is the last slide, and I kind of think of it this way. I mentioned it before too. You're almost in a battle against the user when you're designing these things. So the way your app will break is if the person who is using it starts using it in ways that you didn't anticipate, and they find ways to break it. So these things become very complex. Apps become complex. There's so many behaviors. You have no idea. Sometimes it's hard to anticipate all of the possible behaviors, which is why we build it, we test it, we then realize we messed something up, we go back to the code and we fix it again. That is a totally normal process. But I think a good mindset to have is you are basically trying to play a game of chess against the user. You're trying to be moves ahead of them, anticipate everything they might do. And that is what you then use to make your algorithmic design so that the algorithm is powerful and can cover all of these use cases. Because basically, you want to write as little code as possible to cover as many use cases as possible. The more elegant and simple the description is, the more powerful it is. So the only way you can write that is if you already know in your head how it should work, and then you can determine a really nice way to solve it. So another way to think about it is you're creating their world. Like that's another way I like to think about products sometimes too, is you are setting the rules for everything the user can do. Every time the user breaks your app or your feature, it's because you didn't realize that you created a certain pathway or a certain set of rules that they could do. You didn't realize it, but you actually, in your specification in the code, you created that path for them to do something that you never expected. And then your whole system starts to break down. So just realize that when you're coding, you're defining, and that's basically the whole point. You are defining what the user can and can't do. You are defining what the application should do. And that's why it's good to start with the testing use cases. Because when you write all of these testing cases, you're thinking to yourself explicitly, what should it do, what shouldn't it do, and in what situations. And then lastly, I want to make a point on hackers. What a hacker really is a user that is more clever than you. So like they're beating you in this battle. They found ways to use your code and use your application that you didn't expect. So actually they went a few steps ahead of you. And maybe if they go a few too many steps ahead of you, they can start doing really bad stuff like stealing passwords or hacking into getting user data that shouldn't be and that they shouldn't have access to. So as a senior engineer, you have to worry about that kind of stuff a lot because well, the users are entrusting you with information, right? It's extremely important that you have all of the security measures in place to make sure that doesn't happen. So even security can be looked at from this like user experience perspective too. I just want to reemphasize this point ultimately. You are building something and the people who are using it in the future, you have to think that you have to put yourself in their shoes, basically, and imagine those imaginary people are here and using the app today. And that thought should inform how you're building it. And that's the last slide here. And I hope it was helpful. So awesome.
And this was actually really helpful and went very much deeper and very much better than I had expected. Thank you so much for these learnings.
Great. Thank you. I appreciate it. All right, I'll stop the recording now and then we can just talk about like more specifics.
Yeah, yeah, man, that was really, really awesome.